My talk today is, broadly speaking, on the importance of incorporating the treatment of dust formation evolution in models of galaxy formation, and in particular in cosmological simulation of galaxy formation. This is the summary, and I hope that you're ready. So, what is cosmic dust, first? Cosmic dust is a component of the interstellar medium. It happens that about 1% of the mass of the interstellar medium in the typical local galaxies is not in gaseous form, but it is in form of small solid particles, which we call dust grains. Overall, dust grains account for about 50% of the heavy elements, mass of the heavy elements. There are two basic things which are important to know about dust in order to their effect, and these are the grain size distribution, which few angstrom up to a few micron, and it is reasonably well approximated by a power law, 5 more or less. And the other thing is the chemical composition. For this, we think that dust grains comes in two main chemical groups. One kind of dust grains, which is made mostly or entirely by carbon atoms, and another kind of dust grains, which instead we call astronomical silicates, whose exact composition is not known, but comprises magnesium, iron, silicon, and oxygen. Now, why dust is so important? Actually, dust is now recognized to be an important active element of the life of the medium, and we can say that dust participates actively to the star formation and feedback processes. For instance, dust heats and cools gas. Also, the surface of dust grains acts as efficient catalyzer for the formation of molecular hydrogen. When dust is present in the interstellar medium, actually this is the main channel for the formation of molecular hydrogen, which is related to star formation. Also, dust has an impact on the dynamics of gas because dust grains are very effective in receiving the radiation pressure. So this is one aspect, but another aspect, which is for sure the one which is most studied, is that dust modifies a lot the way in which we perceive astrophysical objects. Again, because dust is very much effective in interacting with the radiation field. The way in which aspect the object is modified is summarized by this picture, this figure of the spectral energy distribution of normal galaxies. Now we have that due to the presence of dust, a lot of energy which is primarily emitted by stars is absorbed in the optical ultraviolet region and then thermally radiated by the dust in the infrared. Okay, so in order to compare models with observation, it is clear that we have to model this dust processing. The problem is that there is a fundamental uncertainty. The fact is that the result depends strongly on the assumed grain composition and on the assumed size distribution. Almost all the computation adopt for this the properties derived from observation, so the so-called average Milky Way dust. Now, if we change in our computation these properties in a not at all a reasonable way, we get a quite different result for the shape of the spectral distribution. For instance, if we change the ratio of carbon over silicon grains or the ratio between large and small grains. So we can say that it would be good to have a prediction for these things from the model in which we want to compare with observation. which are the ingredients necessary for this to do this. We need to understand at some level the life cycle of grains in the interstellar medium. This is, in some sense, an extension of the chemical evolution, because what really happens is that when stars evolve, they inject the interstellar medium their products, their metals, their only in part form of gas, but a substantial fraction of the ejector are ejected in form of solid particles, directly in form of dust grains. In particular, this happens very important way for the metals which enter into dust composition. When these grains produced by stars are in the stellar medium, they are then subject to evolutionary processes which affect quite a lot their abundance, their composition, their size distribution. The main processes are listed here. We have, first of all, accretion, which is the process in which metals, which are in the gaseous form, can deposit on the grainous surface due to collision with the grainous surface. This is a surface process, and therefore it is more important for small grains. In some sense, we have also the opposite process. If the collision between the particles and the grains are energetic enough, in this case, rather than atoms, they don't stick on the surface of the grains, but actually they do the opposite thing. They erode the grains. In particular, thermal sputtering, which this is sputtering, sputtering, and thermal sputtering, which is sputtering due to the thermal motion of ions, becomes very quickly important at temperature higher than a few times 10 to the 5 Kelvin. Also, we have collision between grains, which can modify the size distribution of grains, because the collision can have two opposite results depending on the velocity of the collision. In the dense interstellar medium, the collision is slow enough that usually they can result in coagulation of the grains. So we produce larger grains from smaller grains. On the other hand, in the diffuse interstellar medium, the collisions are quite fast, and the result is the shattering of grains into smaller pieces. So we produce from large grain, we produce more smaller grains. Now, this life cycle for many years have been studied, and not very actively, actually, only in the context of monolithic galaxy or one-zone galaxy formation model, the one usually adopted to study in detail the chemical evolution of galaxies. And in most cases, only the total abundance of grains was produced, but nothing about the size distribution. Actually, the size distribution is probably even more important than chemical composition to compute the radiative effect of grains. And also, as another point to notice, is that to properly compute the dust evolution process, we need to have an idea of the size of the grains, because the efficiency of the various processes depends actually on the size of the grain. Only very recent year, a few groups started to incorporate this computation of these processes into simulation, including our own group. In most cases, it has been used a result pointed out by Hirashita in 2015. He proposed the so-called two-size approximation. Hirashita showed that it is possible to capture the main features of dust evolution just considering two representative sizes of grain, because the processes which I have mentioned operate effectively only on a certain range of sizes. So the whole problem is divided considering just two representative grain sizes, which we call large grain and small grains, with a boundary at about 0.3 micron. This, of course, is a very interesting result for simulation because it is numerically much more cheap to consider just two beams for the size distribution rather than many beams. Before digging into some details on how we can implement these processes in simulation, let me remind you quickly how SPH simulation in particular works. In this kind of simulation, everything is sampled by what we call numerical particles. The name particles is somewhat misleading because these particles actually represent each really huge amount of matter, say at least 10 to the 3, 10 to the 4 solar masses, or even more. Now, in a simulation, we have dark matter particles, which respond only to gravity, but to produce a galaxy, we need also particles to represent the baryonic component of the system. So we have particles to represent gas, and these particles respond both to gravity as well as to hydrodynamical forces. And we have stellar particles, which respond also to gravity. Actually, stellar particles at the beginning are not present, and they are spawned during the evolution of the system from the gas particle when star formation occurs. Now, the point is that most processes which are relevant to produce galaxies, in particular star formation, stellar feedback, and Gian feedback, occur far below the resolution that we can have in a simulation. And therefore, all these processes are not treated from first principles, but they are introduced using sub-resolution prescriptions, which usually means considering particles which are multi-phase. I will say more on this in a moment. So, in some sense, we can think to galaxy formation simulation as extremely CPU time-consuming semi-analytical model, in the sense that they use prescription not very different from semi-analytical model. The main advantage is that in this case we have to some extent resolution, spatial resolution, much more spatial resolution. To give you some feeling on how this super-resolution prescription works, I tell you something about our best super-resolution model for star formation, which we call MUPI. Now, in this model, when a gas particle is cold and dense enough to form stars, they are treated as a multi-phase system, which means that they are treated as a system comprising 3 components: cold gas, hot gas, and a virtual stellar component. Now, these components exchange mass and energy according to some rules, which are represented by differential equations. These differential equations are solved in a numerical way over many times. So when enough matter is accumulated in the virtual stellar component due to the evolution of these system equations, the gas particle creates a new stellar particle, inject into the surrounding medium a new stellar particle, and the mass of the gas particle is reduced in a corresponding way. So, as I say, this is really very similar to what happens in a semi-analytical model, but we have a local semi-analytical in each stellar particle. How we incorporate the dust life cycle in this framework? Now, if we make a zoom of the simulation, we have can think to a gas particle surrounded by one or several stellar particles. All these particles exchange masses because, well, at the beginning, the star particle is created from a gas particle. And when the star evolves, their stars it is taken into account the fact that the stars give to surrounding medium the product of stellar ejecta, which are distributed to the surrounding particles. Now, we have extended, this is standard in the treatment of chemical evolution in simulation, but we have extended this because now we consider that the part of the ejecta are not given to the stellar part, to the gas particle as a form of gas, but in form of solid particles. Therefore, we have complicated the structure of the gas particle to take into account also a budget of mass, which is in form of large dust grain and small dust grains. And we have introduced rules to exchange mass between these two dust components, and also to exchange mass between the real gas component of the gas particles and the what is actually representing the solid state part of the gas particle. So in total, in our simulation, we follow the abundances of 4 kinds of dust grains. We have carbon, small and large grains, and silicate, small and large grains. Okay, this is how this is done. This is done by evolving in time, over time steps, the amount of mass in large and small grains, and also the amount of mass in gas. With this kind of equations, in which there are time scales for all the processes, every processes, dust processes which we are taking into account. These time scales are computed, depends on the local conditions, local physical condition, and are computed accordingly. Another process that we have now included in the simulation is an additional contribution to hot gas cooling. This is due to the presence of dust grains. When in hot plasma, dust grains manage to survive, as long as they manage to survive, the fact that there are collisions between electrons and ions, which on one end can erode the grains, but also give energy. In exchange, there is some heat, some energy is given from the gas from the ions to the grains. The grains are heated by this collision, and the energy which is absorbed is radiated in the infrared region, and therefore is effectively lost by the system, because the medium is usually quite transparent to infrared photons. So this is a plot which shows a comparison between the cooling function due only to gas processes, in particular Bremsstrahlung and line metal cooling, with the possible contribution due to dust grain. Now, in this plot, probably it is exaggerated because it was computed many years ago using a large ratio between the mass in dust and the mass in gas. But in any case, even with a more realistic ratio, this contribution can be very important because it rises steeply at high temperature. This is on one hand. On the other hand, when we take into account that dust subtract some gas metal, we have the standard cooling, the cooling due to metal line emission, is reduced to some extent. So we have two opposite consequences of the inclusion of dust in the system. And we take into account both in our simulation. Well, after this quite long introduction, it's time to show you some result of this framework. The first paper in which we applied this theoretical framework was this one, 2018, in which we applied it to simulation of galaxy cluster formation. zoom-in cosmological simulation. For instance, this figure here shows the evolution for one of the 4 clusters we simulated of the content. These maps are maps of for the content of large grains and small grains. But let us see some more quantitative plot. In particular, I want to concentrate on this one. Okay, this plot shows the evolution in redshift and look-back time of the amount of dust, total dust, divided by, normalized by the mass of the cluster. So the mass fraction of dust. As you can see, after initial creation of dust, in our fiducial model, which is the brown one, okay, and most of these models, the dust tend to decrease over time. And this happens because of the intercluster medium become hot, and sputtering is very efficient in a hot intercluster medium to destroy dust. So the dust fraction tend to decrease over the run of the simulation. Another interesting point to notice is the effect of the interstellar medium processes. When we switch off this, we switch off accretion, scattering, coagulation, we get this line here, which is, I would say, purple. And as you can see, the final amount of dust is reduced by a factor 2 or 3, which means that the processes in the stellar medium are even more important than the direct creation of dust to explain the final dust content in this kind of system. Another interesting point to notice from this simulation is the evolution over time of quantities which tell us something about the dust mixture. So again, the brown is the fiducial model, and at the end we get values for the ratio of small grains over large grains, and also for the ratio between silicate grains and carbon grains, which are quite similar to those obtained, assumed in most radiative transfer computation, which, as I said before, are based on the properties, averaging properties of dust in the Milky Way. But if we look at the earlier time, for instance, redshift 2 or 3, we get that both ratios are significantly different, much smaller. So the radiative transfer computation, actually we included in the paper radiative transfer computation in this condition, gives quite different results. In this paper, we have also produced some comparison of the dust content from the simulation with the observation. Actually, there are very little reliable observation for the dust content in cluster. Probably the best one is this one made in this Planck collaboration paper, in which by combining Planck, Herschel, and IRIS data, derived this data point, which are determination of the dust content within the Planck beam over the mass of the cluster for a large sample, for large samples of cluster. And this is compared with what we get from our simulation, the evolution of this ratio for the 4 clusters we simulated. The fiducial model are the solid color lines in various colors. And as you can see, all these simulations underpredict by a factor between 3 and 4 the dust content with respect to observational data. Now, if we believe to this observational data, the only way we have to improve this match is to decrease the sputtering efficiency with respect to the standard values, which are usually derived from a laboratory measurement or from Monte Carlo simulation of the impact of ions on solid bodies. I will now show some results from this very recent paper published a couple of months ago, in which we have studied the evolution of dust in zoom-in cosmological simulation for the formation of a single Milky Way-like disk galaxy. The general idea of this paper was to study the effect of several assumptions and approximation. So we have run, beside our fiducial model, several variations of it. I will concentrate in the following just on a few of them, the one highlighted here in yellow. And also I want to point out that each of these cases have been run 6 times, introducing every time very small perturbation on the initial condition. Why we do this? We do this because it is now quite clear that when we repeat the same simulation, exactly with the same code, we can obtain results which differ in a not negligible way, let's say. And this is on one hand related to the real chaotic physical nature of an body system, which is made worse by numerical issues, such as the non-deterministic nature of parallel reduction or the stochastic algorithm, which are present when treating baryonic processes. Now, we want to distinguish the effect of this butterfly effect from that of real differences in the assumption. And to do this, we introduce in the initial condition extremely small perturbation. So here and in the following figures, I will show evolution of quantities integrated within 10% of the galactic dark matter halo, which is a conventional way to define the galaxy in the simulation. But for each of the model, I will show we have a line which refers to the average main value for the 6th repeated run and a shadow area with the same color, which covers the whole dispersion of the 6th run. So this, you can think to this shadow area as the uncertainty in the run. And this is usual to distinguish butterfly effect differences from real difference due to the assumption. In this first plot, we show the evolution of the gas content in the galactic region for the fiducial model and for a model in which we have switch off the dust cooling process, or a model in which we have switch off the sputtering dust destruction. So we have that in the first case, we have less gas in the region of the galaxy, and the last case, we have instead more gas. In the first case, we have less gas because without cooling, less gas is able to make its way to the galactic region. And the opposite happens when we switch off sputtering, because without sputtering, we have more dust and therefore more dust cooling. This, of course, has consequences for the star formation, the rate, and for the final stellar content, for the stellar content of the galaxy. We have that if we neglect cooling, dust cooling, sorry, we have a lower star formation rate and therefore less stars in the galaxy, and the opposite happens if we neglect the dust sputtering, because we have more cooling in this case, and therefore more star formation and more stellar content. So the point to remember is that although we are not considering here all the possible effects of dust, or even the couple of effects that are included in this simulation, are able to affect galaxy evolution in a significant way. Another thing that I want to show you is the relative importance, related to the relative importance of direct formation of dust from stars and formation of stars in the interstellar matter processes. Here we have a comparison for the dust content as a function of look-back time for the fiducial model in black, and for a model in which we have instead switch off all the accretion processes, and therefore all the processes of growth of grains in the stellar medium. What we have is that in the latter case, the galaxy and its history with a factor 3 less dust, which means that from some point about redshift 1, the accretion wins over stellar production in the contribution to dust. And in the final galaxy, about 70% of the dust is not produced directly from the stars, but it is produced or increased in the interstellar. As last thing, I show you some comparison with data. Now, we have not devoted in this paper much space, much room to comparison with data. The only thing that we have done is to compare with this observation by Relagno et al. 2020, who fitted on a pixel-by-pixel basis images from the near to the far infrared maps of 3 nearby spiral galaxies. And therefore, in this way, they have been able to derive dust mass maps, and also they estimated the mass share of small and big grains. We have compared just with this data. What we have to take into account that there is no particular reason for our model to be identical to any of these galaxies, and therefore we have not adjusted in any way any of the parameters. We have just compared the model as the fiducial model as it is. Despite this, the comparison is really very, I would say, impressively good. This is shown here. For the year we have the profile, radial profile of the dust over gas ratio for our model, fiducial model, at 2 different resolutions. There is not very much difference between resolutions, actually. Dispersion compare with the data points with error bars, which are the observational derived quantities for the 3 spiral. So the match is really very, very good. Also, we have a comparison of the profile of the small over large dust grain ratio, mass ratio, for the 3 galaxies, observed galaxy, and for our model. Again, we have really a very good match, at least for 2 of the 3 galaxies. Well, this is all I wanted to say about the topic, and I leave you with a summary of the main point of my